Poiseuilles formula for fluid flow. So if a liquid is flowing at a steady flow in a tube such as this one, the volume of the liquid that is issuing out or that is flowing out per second is going to be affected by three things. First of all, the volume flow rate, which we're representing here as volume, divide that by time, is going to be affected by the viscosity of the liquid. The volume flow rate is also going to be affected by the radius of the pipe in which it is flowing, and the volume flow rate will also be affected by the pressure gradient as the fluid is flowing through. And the pressure gradient, in this case we're talking about pressure P. This is standing for pressure difference, divide that by the length. This L stands for the length of the pipe. Pressure gradient is simply the change in pressure of a liquid in a tube of 1 meter. The change in pressure being P2 minus P1, which is represented by P, divide that by the length of the tube, which is L. So it means that we mean by pressure gradient, the change in pressure of a liquid in a tube of 1 meter. So when we are talking about steady flow of a liquid through a tube like that, according to Poiseuilles formula, it is such that this steady flow is affected by these three factors, which is the radius, the pressure gradient, and we have the viscosity. Now combining these three gives us something like that, volume flow rate, the rate at which that fluid is flowing at steady state condition, is directly proportional to the coefficient of viscosity, the radius of the pipe, and the pressure gradient. Now, to remove this proportionality sign, we introduce a constant of proportionality which we have called K, and this gives us coefficient of viscosity to the power X, R to the power Y, and this to the power Z. And now we need to find out what the value of X, Y, and Z are. And after finding out the value of X, Y, and Z are, then we write the proper formula for this. So we are going to use dimensions to find the values of X, Y, and Z, so that we end up finding the correct equation for this thing. So we'll begin. So using dimensional analysis, we know that we need to find the dimensions of V. Divide that by the dimensions of time is going to give us K. Now K, since K is constant, it means it is dimensionless. Of course, this coefficient of viscosity to the power X has dimensions times R to the power Y, multiply that by the dimensions of P, divide that by the dimensions of L, which is the length, and this is all to the power Z. So we have the power Z up there and the power Z up there. So we continue. So of course this is volume. Volume is L to the power 3. So this is L to the power 3. Divide that by the dimensions of time is capital T, which is time. That is going to be equal to the dimensions of the coefficient of viscosity. Now, to get the dimensions of coefficient of viscosity, we are going to have to do some side work. We all know that coefficient of viscosity by definition is given by force, divide that by area times the velocity gradient. So force is given by mass times acceleration, divide that by cross-sectional area. This is area times the velocity gradient, V2 minus V1 over L. So let's get to the dimensions of mass. Dimensions of mass is capital M. Multiply that, the dimensions of acceleration is given by Lt to the power negative 2, because acceleration is given by velocity over time, which is Lt to the power negative 2. Divide that by area, which is L squared. Multiply that by change in velocity, V2 minus V1 gives us velocity. Velocity is Lt to the power negative 1. Divide that by L. L is, the length is L, like that. So we know that this L will go with that L, and then we shall end up here with M, L, T to the power negative 2, divide that by L squared, multiply that by T to the power negative 1. And then to make this all universal, We have m, we have L up here and L. The laws of indices, this is 1 minus 2. This gives us L to the power 1 minus 2, which gives us negative 1. Then we have capital T here. The law of indices, T, when you divide indices of the same base, you subtract the powers, negative 2 minus negative 1. This gives us negative 2 plus 1, which gives us negative 1. So these are the dimensions of this. I have a separate video on how to find dimensions of quantities. I'll put the link in the description below. So back to what we were doing. The dimensions of this are, we have m, L to the power negative 1, T to the power negative 1, and these are the dimensions of the coefficient of viscosity to the power x. Multiply that by r. R is L to the power y, because r is radius, it's a length. And then we have also pressure gradient. Of course, now pressure over L, let's summarize it and bring one thing here. Again, we're going to do some side work for P over L. So we have pressure over the length. The pressure, we know that pressure is given by force over area. That is pressure, divide that by L, the length. Now we all know that force is given by mass times acceleration, divide that by area. All this is divide that by the length. So finding the dimensions of mass is capital M. Dimensions of acceleration is L t to the power negative 2. Divide that by the dimensions of area. That is going to give us L squared. And all this, we divide all this by L, the length of the pipe. So we simply simplify this. This becomes m L t to the power negative 2 over L. Multiply that by 1 over L. This L cancels with that L, and you end up with your answer as m. This is L to the power negative 2, m L to the power negative 2. Then you have t to the power negative 2. So those are the dimensions of P over L. So this is going to become m L to the power negative 2, t to the power negative 2. And this is to the power z. So from this we have something like this. We have L to the power 3, t, this is to the power negative 1, is equal to capital M L to the power negative 1, t to the power negative 1, this is to the power x, multiply that by L to the power y, multiply that by m L to the power negative 2, t to the power negative 2, and this is to the power z. So let's compare the powers. We start equating the corresponding indices. Now let's look at the indices where we're having for those of m. You look at m on this side of the equation and that side of the equation. So when it comes to m, this way there is nothing, so 0 is going to be equal to, let's look at m this side of the equation. We have x, then we have another m here, it is to the power z, so it's going to become x plus z. That's equation 1. Then let's get to L. Let's equate the indices for L. When you get to L, this side of the equation we have L to the power 3, so we have 3 there. So it's going to become 3. It's going to be equal to, when you come to L this side, we have L to the power negative 1. Negative 1 times x gives us negative x. Then you have L here to the power y, so it's 1 times y, which is y, plus y. Then we have another L here to the power negative 2. Negative 2 times z is going to be minus 2z. That's another equation 2. Then you come to t. You equate the indices of t, and for t, we look at this side of the equation. T has negative 1 this way. Negative 1 is going to be equal to t this way is negative 1 times x is going to become negative x. That's going to give us then t here negative 2 plus z. Actually it is negative 2z, so it's minus 2z. So is with negative 1 is going to be negative x minus 2z, giving us the third equation. So you're going to solve these three equations simultaneously to get the values of x, y, and z. To cut the long story short, if you look at equation 1 and equation 3 and you solve them, you're going to get negative z as 1. And then from equation 1, after getting z as 1, you'll find that your value of x will be equal to negative 1. Then again, when you continue from equation 2, you'll be able to get to, after substituting, you'll get your value of y as 4. So after getting these, solving those three equations simultaneously, so this becomes volume flow rate V over T becomes the constant K times this is to the power negative 1, the value of x here is negative 1, multiply that by r, r is y is to the power 4, multiply that by the pressure gradient P over L, and this P over L is to the power z, which is 1. So now when experiments were held, it was found that the value of K was equivalent to pi over 8. Therefore, this expression becomes V over T is going to give us our value of K, which is pi over 8. Multiply that by the coefficient of viscosity to the power 1. Multiply that by R to the power 4 times the pressure gradient to the power 1. So this becomes, if you have to rearrange this equation, this V over T is going to become V over T is going to be equal to pi R to the power 4 times P, P being the difference in pressure, divide that by 8 times the coefficient of viscosity times L. And in this case, P is simply the change in pressure. That is P2 minus P1. Now this expression, showing the volume flow rate being equal to this, is what we are calling Poiseuilles formula. And it only applies for steady flow, or call it laminar flow in liquids. Experiment to determine coefficient of viscosity using Poiseuilles formula. So we're going to use Poiseuilles formula, a formula that we derived in our previous session, to find the coefficient of viscosity using this setup. If we are to look back on what we derived in our previous formula, we say that the volume flow rate is given by pi r to the power 4p divided by 8 times the coefficient of viscosity times r. Now, you realize that what we want here is this. We want to find the coefficient of viscosity, but we are trying to find the coefficient of viscosity using this formula. So it means that when we try to find the coefficient of viscosity using this Poiseuilles formula, and this is the setup of our experiment, it means that in this experiment we are supposed to come up with the following. We need to find the volume flow rate using that apparatus. After finding the volume flow rate, of course, we are supposed to find the radius of the pipe we are going to be using, the length of that pipe we are using. These, of course, are constants. Then also we are supposed to know the change in pressure. Then we shall be able to find this. So looking at our apparatus right here, we are having this as a constant head tank. The use of this constant head tank is to ensure that there is a steady flow of liquid. From our tap here, you see that we are having some water that is coming in here. When it flows in here, it is only the water that comes through the tank, part of it is let into this beaker or this container right here. So this is a constant water tank, and the purpose of this constant water tank is to ensure that there is a steady flow of liquid through this capillary tube. Then we have this thermometer. Of course, definitely we are supposed to measure the temperature of this liquid, because as we are trying to find coefficient of viscosity, like we had discussed earlier, is affected by temperature. So because coefficient of viscosity is affected by temperature, we definitely have to measure the temperature of the liquid. Now we also are supposed to take record of the capillary tube's radius. Now taking record of the capillary tube's radius, we can use a traveling microscope or a micrometer screw gauge to do so. So by measuring this, we are trying to find the value of R, which we are going to use in our equation. Then also we're supposed to take the temperature. We need to know the temperature this liquid is at. And also we have what we call the waste pipe. This waste pipe is simply a pipe that you can adjust. You can either push it up. Of course, if you push this pipe up, it means that the water that is coming in here will have to raise to that level of the pipe before it flows out to be wasted. Or if you want, you can pull this pipe downwards, and if it comes downwards, it means that this water that is flowing into this constant head tank will have to rise up to the level of that pipe, and then it follows back out of the pipe. Now the use of this waste pipe is more like to regulate the height of the water here. So we can regulate this value of H, the height of the water, by regulating the pipe by pulling it up or down. And by regulating this height, we are in essence regulating the pressure exerted by this water, since we all know that pressure in liquids, it is influenced by height or by depth of the liquid. The deeper the liquid, or the greater this height, the greater is the pressure. And if this height is less, it means that the pressure is also less. So now to get started with this experiment, what we do definitely, like from our equation, we need to get the volume flow rate. The volume flow rate V over T is obtained by collecting this liquid in a known time T. In other words, you're going to collect this liquid, you're going to get a stop clock, and you measure how much liquid, you measure a specific amount of time. Let's say you're going to let this thing to flow for like 1 minute. Then after getting, you close the tap, and then you get how much volume of liquid has flown in that 1 minute. So you get this volume of the liquid that has flown in 1 minute. So you get the volume, divide that by the time, and then you're able to get the volume flow rate of this. Now when we are finding that volume flow rate, you are doing it at a certain height H. So what you do is that you adjust this waste pipe so that you obtain a new value of H. After obtaining the new value of H, get another volume flow rate, V over T. What am I trying to say? What I'm trying to say is that you get the volume flow rate for different values of H. And how do you get the different values of H? By adjusting the waste pipe. Either you push it up so that the value of H increases, or you push it down so that the value of H reduces. You get the value of V over T for different values of H, and after doing so, you plot a graph of volume flow rate against the height, because these are the two things you're varying. As you're getting volume flow rate and the values of H, you're going to plot a graph of V over T against H. So you plot a graph of volume flow rate against height, and as you plot this graph, you realize that when this value of H is still low, the volume flow rate will be low. But as you go on increasing this height using this waste pipe, as you increase this height, it means that this is going to increase the volume flow rate, or the rate at which the rate of the volume flow rate into this is going to increase up to a point whereby it's going to become a turbulent flow, because of the height has increased so much that now there is too much pressure going through. When the pressure is too much, it turns from laminar flow to turbulent flow, and the volume flow rate there is going to remain constant regardless of the height. So this is the graph you plot as a result from the experiment you've carried out, and after plotting that graph, you go ahead and find the gradient of this graph. Let's get into our calculations and see how the gradient of this graph is going to correlate, and it's going to help us to find the coefficient of viscosity of this liquid. Now this is Poiseuilles' formula, the one that we are using to find the coefficient of viscosity of the liquid. This is what we're trying to look for right there. But we know that this P here is the pressure difference. Now by pressure difference, we're talking about the pressure that is caused by that height of liquid. When that pressure, we have the pressure on top there, and then the pressure at the bottom. We say that pressure in liquids depends on depth. So now the difference between the pressure at where this capillary tube is and the pressure at the top there, that difference in pressure is what we are dealing with, calling the pressure difference here, which is given by the height of that times the density of water times the gravity, which is what we have substituted. Where there is pressure there is what we've put here, height times density times gravity. Now that we have this height times density times gravity, remember when we were carrying out this expression, we were varying the volume flow rate with the height. And so when we put this value of h outside here and the volume flow rate here, you realize that this expression is in the form of y is equal to mx. We know that the general equation of a straight line is given by y is equal to mx plus c, where c is the is the y-intercept. This value of m for a straight line equation is the gradient. It is a constant, and if you look through here, pi is a constant, the radius of this tube is a constant, it's not changing, the density of water is a constant, the gravity is a constant, 8 here is a constant, the coefficient of which we are looking for is, this is what we are looking for, then L. The length of the tube is also a constant, it doesn't change. So it means that if we equate this m to this, then we'll be able to get the coefficient of viscosity. Because remember, this value of y so happens to be the v over t, and this value of x so happens to be the h. And from our graph, we plotted a graph of volume flow rate, which is acting as our value of y, against h, which is acting as a value of x. So this is a graph of y against x, and the gradient of that graph is what we are calling the gradient m. So this is like, this is y, that is our value of x, and our gradient here is m. So likewise, if you look at this, this is the volume flow rate, which is that axis, against the value of h, which is this axis, and so it means that our value of m, which is the gradient, is equivalent to this expression here, which is this. So it means that this expression we've got is equivalent to our value of m right there. So if we equate our value of m, the gradient of this graph, to this expression, then we'll be able to get the coefficient of viscosity. So that is exactly what we do. The slope, which is m, is equated to the rest of this whole thing, which is pi r to the power 4 times the density times gravity divided by that by 8 times the coefficient of viscosity times L. And when we make the coefficient of viscosity the subject of the formula, like we've done in the next step, then from there we are able to get the coefficient of viscosity using this expression. And that is how we find the coefficient of viscosity using Poiseuilles formula. In this session, we are going to look at worked examples, or we are going to look at some solved problems regarding Poiseuilles formula. Coming up. We get started with this. A liquid flows steadily through a horizontal pipe of length 3.2 meters. If the amount of liquid collected at one end is 6 grams per second, what is the pressure difference between the two ends of the pipe? Let's draw that pipe. So this is the pipe we are talking about. This pipe has a horizontal length, so the length of this pipe is 3.2 meters. And at one end, let's say there is this end and there is that end. At this end there is a pressure, and that end also there is a pressure. The question is asking us to find what is the pressure difference between the two ends of the pipe. What is P2 minus P1 equal to? And then after finding what P2 minus P1 is, then hence calculate the pressure gradient. Pressure gradient is P2 minus P1, divide that by the length, which happens to be 3.2. So we need to first find this, then after finding that, we find that right there. And of course, the other information is that at what the liquid collected at the end is 6 grams per second. Now 6 grams per second, it's 6 grams, that is mass. So the mass per second, mass over time, that is the 6 grams per second, meaning that the mass flow rate, or the amount of the mass of the water that is flowing every second, is 6 grams of water per second. So this is the mass flow rate. So of course we're supposed to be using Poiseuilles formula to find this, then eventually we find that. So now where do we start from? Let's first quote this formula. Poiseuilles' formula says that V over T, which is volume flow rate, or the amount of volume of water flowing per second, is given by pi r to the power of 4 times the pressure difference, which is this, P2 minus P1, divide that by 8 times the coefficient of viscosity times the length of the pipe. Now, we derived this in our previous session, and now we're just going to use it. So now the question is, we need to make this the subject of the formula, the pressure difference, because it's what we need to find first, according to the question. So making P the subject of the formula is going to give us P being equal to 8 times coefficient of viscosity times the length times the volume flow rate, V over T, divide that by pi r to the power 4, times pi times r to the power 4. Now that we have made P the subject of the formula, which is the pressure difference in this case, so now we need to go ahead and find it, because the question requires us to do so. But now if you to look at this question, if you look for us to get the P, the pressure difference, according to what the question is telling us, that what is the pressure difference, you realize, yes, we have the 8. We have the coefficient of viscosity of this liquid. According to our question, it has been given to us as 0.92 newtons per meter. We have the length of the pipe. The length of the pipe was given to us as 3.2 meters, right there, 3.2. So we have this, we have the length. We need the volume flow rate. Now the volume flow rate is not given anywhere. Of course, we know pi is a constant. We have the radius of the pipe. The radius of the pipe is 7.5 millimeters. We have that. So for us to get the pressure difference, you realize that we are missing the volume flow rate. So we need to first find the volume flow rate so that we are able to have everything, and we just simply substitute here and we're able to get the pressure difference. But now the volume flow rate we do not have, but what we have is the mass flow rate, which is 6 grams per second. So meaning that if we can use this mass flow rate to get the volume flow rate, and we come and put it right there, and then we will be able to find the pressure difference. So now, if we may call it a bit of side work or something, but we need to first find this volume flow rate. And since we have the mass flow rate, we can move from the mass flow rate to move to the volume flow rate. So let's begin by first finding V over T. First of all, we know that density is given by mass over volume. So it means that if we make mass the subject of the formula, it's going to mean that mass is going to be given by density times volume. Now this is mass is equal to density times volume. So mass being equal to density times volume, if you look at our question, what we have is this. We have mass, divide that by time, mass flow rate. So what we do to this is that we divide both sides by time. So we divide this way by time, we divide that way by time. And when we divide m over t, now we have an expression for mass flow rate. And so mass flow rate is going to give us density times V over T. Now V over T is the volume flow rate. Volume, divide that by time. And that is exactly what we're looking for. So it means that mass, divide that by time, is 6 grams per second. Is going to give us the density. Now we're dealing with the density of the fluid. In the question, the density of the fluid is 1.2 times 10 to the power 3. So this is going to be 1.2 times 10 to the power 3 kilograms per meters cubed. Multiply that by the volume flow rate, which is V over T. So when we make V over T the subject of this formula, we end up with volume flow rate giving us 5 times 10 to the power negative 6. So this is the volume flow rate. Now that we've gotten V over T, now we can go ahead and find the pressure difference. So getting back to our expression, to get the pressure difference, this is going to become 8. Multiply 8 by the coefficient of viscosity. Coefficient of viscosity is 0.92 newtons per meter. So it's 0.92 newtons meter. Multiply that by the length. The length of the tube, according to our question, is given as 3.2 meters. So the length of the tube is 3.2 meters. Multiply that by the volume flow rate. We got our volume flow rate as 5 times 10 to the power negative 6. So that is 5 times 10 to the power negative 6. Divide all that by pi, which so happens to be 3.14. Multiply that by the radius of the tube. Now the radius of the tube is 7.5 millimeters. Now 7.5 millimeters, we convert this to meters so that it's in the right standard units. Converting 7.5 millimeters to meters is going to be 7.5. Multiply that by 10 to the power negative 3. And this is to the power 4. So upon computing all that, our pressure difference is going to be given by, it's 11,846.849 pascals. That's our pressure difference. So we've answered the first part of the question. The first part of the question required us to find the pressure difference between the two ends of the pipe, which we have just discovered. So we go ahead and calculate the pressure gradient. Therefore, after getting the pressure difference, so we go ahead and find the pressure gradient. So in this case, the pressure gradient is going to be the pressure difference divided that by the length of the tube, which is going to be 11,846.849 pascals. Divide that by 3.2 meters. And we shall end up with 3.7 times 10 to the power 3 as our pressure gradient. An empty vessel which is open at the top has a horizontal capillary tube of 20 centimeters and internal radius of 1 millimeter. So we have an empty vessel right there. The question says that it is having a horizontal tube. It is open at the top right here, and it has a horizontal capillary tube. The horizontal capillary tube here has a certain length of 20 centimeters. Of course, 20 centimeters, we convert that, it's going to become 0.2 meters. And internal radius of 1 millimeter. So this is the length of the tube. So the radius of the tube is 1 millimeter. Of course, 1 millimeter, we convert that to meters as well. And that was going to give us 1 times 10 to the power negative 3 meters. Internal radius of 1 millimeter. It is protruding from one of the side walls immediately above the base. That's what I've just drawn. Water flows into the vessel at a constant rate of 1.5 centimeters cubed per second. So this is centimeters cubed per second. Centimeters cubed is volume per second. So it means that the volume flow rate, let's call it V over T, is 1.5 centimeters cubed per second. Now let's convert this centimeters cubed to this SI units. These centimeters cubed, we convert them to meters cubed per second. So it means that our volume flow rate is instead going to be, that will be 1.5, divide that by, and this we will have converted this to meters cubed per second. Now the question continues to say that water flows into the vessel at that constant rate, and now they are asking us at what depth does the water level stop rising? Assume steady flow. Of course, when we are talking about steady flow, we are talking about Poiseuilles formula, and this is the height of when water is coming in. It's flowing in at that rate. So water is flowing into this thing at that rate, and as it's flowing in, it is protruding out of here. So definitely this is a very small capillary tube, and so it means that as water is flowing in at this rate, part of that water is flowing out of this capillary tube as it goes out. This question is asking that at what depth does the water level stop rising? Now, at what depth that the water level stop rising, meaning assuming steady flow, it means that if this height is to be constant, and it is not rising, the water levels are rising, that would logically mean that the amount of water coming in is the same amount of water going out. In other words, the rate at which water is coming in, the volume flow rate coming in here, is the same volume flow rate going out. So definitely, if the water is if this height is to be constant, that is, if this height is to be constant, it would mean that if we are having 1.5 centimeters cubed of water coming in, it would mean that we are still having 1.5 centimeters cubed of water going out, meaning what is coming in is what is going out, and so this height is constant. So if we are going to use Poiseuilles formula, it means that as far as the pressure difference is concerned, we are looking for the height when this thing is the constant height when it's the same water coming in and same water going out. So how do we go about this? First, we quote Poiseuilles formula and we go ahead and find that height difference. So we know that Poiseuilles formula V over T is given by pi r to the power 4 times the pressure difference, divide that by 8 times the coefficient of viscosity times the length of the pipe. So this is going to be pi. As we continue, pi, this is V over T, is giving us pi times the radius of the pipe, which is r to the power 4. Multiply that by, now P here represents the pressure difference. So it means that the pressure difference, this height of water, this pressure of water, we convert that to, it's supposed to be height of that times the density of the water times gravity. Divide that by 8 times the coefficient of viscosity times L. Now in this case we are interested in the height. We are interested in the height that is going to make this constant, that when the volume flow rate is such that it's 1.5 centimeters cubed are the ones that are coming in here. What is the volume flow rate? What is the height that is going to correspond to that volume flow rate? In other words, when this height is constant, if this height is to be constant and water flowing in is the same water flowing out, what volume flow? Battery, no space. So the pressure difference here, which is maybe the pressure at this level minus the pressure at that level. The pressure difference is given by height times density times gravity. So the height of the liquid column that is going to be produce that pressure is converted into this. And now we go ahead and find the height. What is that constant height that is going to enable this volume flow rate to be constant all through? So we make h the subject of this formula in this case, since we are looking for the height. So h, to make h the subject of the formula, is going to become 8 times this the coefficient of viscosity times the length of the pipe. Multiply that by the volume flow rate. Divide all that by pi times r to the power 4. Multiply that by the density of the water, multiply that by gravity. So now that we have made h the subject of the formula, we go ahead and substitute in the rest and we get the value of h. So this is going to become 8, multiply that by the coefficient of viscosity. Now according to our question, the coefficient of viscosity is 1.0 times 10 to the power negative 3, so it's going to be times 1.0 times 10 to the power negative 3. Multiply that by the length of the tube. The length of the tube, according to our question, the length of the tube is 0.2 meters right there. So this is going to be times L, which is times 0.2. Multiply that by the volume flow rate. Now we got the volume flow rate, we converted it to meters cubed, according to our question here. So it's 1.5 over that. So in other words, it's 1.5. Multiply that by 10 to the power negative 6. The volume flow rate, divide that by the pi, which is 3.14 times the radius to the power 4. Now our radius was converted to meters, which is 1, times 10 to the power negative 3, and this is to the power 4. Multiply that by the density of water. Of course, the density of water is 1000 kilograms per meters cubed. Multiply that by gravity, which is multiply that by 9.8. 1. And so the answer we end up with here as our value of h, or as our height, is 7.8 times 10 to the power negative 2 meters. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.